Hello everybody and welcome to the last tutorial video of the year. Pew 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 pew. Anyway, it's been a long year, guys, and we're going to end with a quick tutorial on trig functions graphs. So what we're going to do is we're going to look at the graphs of sine functions, cosine, and tangents today, and we're going to use the unit circle to help figure out what these graphs are, why they look the way they do, and then your guys' assignment today is to learn a little bit more about some of the behaviors of these functions. So let's get started with the sine function. So what I'm going to do here is you'll see that I've listed in the x column all of these radians. Now what you'll remember from these radians, or these radians should seem familiar because these are all the radians starting at 0 that work their way around the unit circle in, again, a counterclockwise rotation. Now you might be wondering why radians and not degrees. Well, when it comes to graphing some of these functions a little bit later on, and for some of you who go through pre-calc and up, you'll realize that shifting these functions and doing all the other things that we normally do with functions that we learned earlier this year are much easier to do with radians than they are with degrees. Really more on that in your next math class. But for now, just believe me when I say that radians is really the way we do inputs, at least for trig functions and graphing. So you'll notice that I've already made the x-axis on these pi. Now if you're wondering how I did that, I pretty much went up to this little graph setting and I changed the step from numbers to pi, and the way you can do that is when you click to type something in Desmos, there's a pi symbol there that you can just insert that, and by doing that it goes from like a number system, so for instance like right now it's like a 1 2 3 whatever, to you can make it a pi system. And you'll notice that this is already set up for radians anyway, so you don't have to really do anything much about that. So just a heads up on that if you do want to make your x-axis reflect the inputs of these graphs. Anyway, so without further ado, let us get started. So when I am doing a sine function, what I'm doing is plugging all of these radians into sine and figuring out what is that output. Well, knowing what we know about the unit circle, sine is the y-coordinates for each of those radians. So what we're going to do is we're going to start with the radian of 0. The sine of 0 is, y value of that is 0. So I'm going to put a 0 next to that. And you'll notice that it put a dot there for me. Let's go to pi to x, pi over 6, sorry. The y value for that is 1/2, so the sine of pi over 6 is 1/2. And there goes the dot there. Now we'll do pi over 4. Pi over 4, square root of 2 over 2. So we'll go ahead and put that in there. For square root of 2 over 2. And we're just going to start filling this in. So let's go. Pi over 3, square root of 3 over 2. Do that next. And pi over 2, we go ahead and get 1. So far what you notice is this is an increasing function. Starting at 0, the points are going up. Now what you'll notice is that it definitely doesn't look like a straight line. It definitely seems that as I start getting closer to pi over 2, it's definitely kind of starting to taper off a little bit. Let's see what happens next. All right, so the next radian is 2 pi over 3. We get a square root of 3 over 2. Now, what you'll notice is, actually, maybe see, I can just copy and paste that. Yeah, what you'll notice is that you have 2 square root of 3 over 2's, and one of the things you'll start seeing is that there's a lot of repeats when it comes to y values here. In fact, the next one after that would be the square root of 2 over 2, which is identical to what you were getting over here for pi over 4. So you'll get a square root of 2 over 2 on this side. What you'll start seeing is kind of like the reverse happen, kind of like almost reflecting over pi over 2. So if I have pi over 6, no shocker here, will be 1/2. And then lastly, pi, if you take a look at that, the sine of that is 0. So a nice little reflection going on in this first part. And really this is just a reflection of the unit circle and the fact that we're just kind of going around it 1 radian at a time. Now we're getting to 7 pi over 6. Now you're getting into negative y territory. Now let's go ahead and go to this negative territory. So for 7 pi over 6, the y value for that is negative 1/2. So I'll go ahead and fill that one in, negative 1/2. And hopefully what you'll notice is there's definitely a pattern going on here. It's 0, 1/2, square root of 2 over 2, square root of 3 over 2, 1, square root of 3 over 2, square root of 2 over 2, 1/2, 0. Now it's 1/2 again. So if you want to guess what the next one is, it's going to be square root of 2 over 2. But this time, you'll notice it will be negative root 2 over 2. So here we go, negative root 2 over 2. The next one, 4 pi over 3, if you guess square root of 3 over 2, you are absolutely right, but don't forget the negative. So negative square root of 3 over 2. And then last but not least, square root of 3 pi over 2. The y value for that is negative 1. So we got negative 1 here. And at this point, you're starting to see that it has decreased. It started increasing, then it started to kind of decrease all the way up into this point. And now, as I continue around my unit circle, 5 pi over 3, you end up kind of wrapping this up. You'll get negative square root of 3 over 2, which is next. The next one after that, y value is negative square root of 2 over 2. So we'll continue that, negative square root of 2 over 2. And then last but not least, we get a negative 1/2 for 11 pi over 6. So we're going to do negative 1 over 2. And then we're back to 2 pi. And to kind of complete this pattern, 0 will be last, because at 2 pi, which is the same thing as 0 degrees, you get back to 0. Now, if I were to continue rotating, so 2 pi plus another pi over 6 and continue, you'll notice that I'll just go through that same loop over and over and over again, which is why when I actually graph y equals sine over x, you'll notice that this graph doesn't just stop at 2 pi, it actually continues on forever and ever and ever in that same sequence, right? In fact, I'll zoom out. All a sine wave is that unit circle unwound, for the most part, rotated over and over and over and over and over again. So this would represent winding it up in a counterclockwise direction as the angles increase forever and ever, because imagine that you're just spinning over and over and over. And then this would represent just the opposite way of spinning. So for instance, instead of spinning counterclockwise around this way, you're spinning clockwise, starting at 0, but going in this case, a negative angle direction. So that is why sine of x has the shape that it does. Now, if you take a look at the unit circle, we're going to do cosine x. You'll notice that cosine really has borrowed a lot of the same values, right? You'll notice that the x coordinates for each of these aren't much different. They're just in different places. So you'll note that if you want to make any predictions, this cosine function probably isn't going to look too much different than the sine function, but it is going to be different. So let's start with a 0. At 0, the x coordinate is 1. So we'll fill a 1 in there. Pi over 4, you'll notice this time I skipped ahead a little bit. We're doing a little less because, you know, that last one took a little longer. So pi over 4, we'll do square root of 2 over 2. So we'll do square root of 2 over 2. Pi over 2, you end up getting 0 for the x coordinate, so the cosine of pi over 2 is just 0. So let's go to 3 pi over 4. So 3 pi over 4, it's now in the negative x territory, so we got negative square root of 2 over 2. Whoops. All right, so let's move to 3 pi over 4. So at 3 pi over 4, we're in the negative x territory now. So we got a negative square root of 2 over 2. So let's go negative square root of 2. And then pi, we get a negative 1 x coordinate. So we'll just go ahead and label it negative 1. 5 pi over 4, the x coordinate of that would be another negative square root of 2 over 2. And I don't know about you guys, but I'm starting to see that same kind of pattern emerge that we had for the sine graph. It just looks slightly a little bit more augmented. So 3 pi over 2, the x-coordinate for that would be 0. And then 7 pi over 4, we'll get another positive square root of 2 over 2 for that x-coordinate, right? So we'll do square root of 2 over 2. And then lastly, 2 pi, we're back where we began. The x-coordinate of that is 1, so the cosine of 360 over 2 pi is just going to be 1. So you'll notice that you kind of have that same kind of like hill valley kind of thing going on, but it definitely looks a little different, that sequence in the unit circle. So 1 started, like at least for the sine, it kind of started at 0, worked its way up, kind of dack down, and then went back to 0. This one looks like it starts more at 1, goes back down to -1, and then goes back up. So they're still bouncing between the same two y values. It's just shifted, it seems like, a little bit. So let's graph cosine. You'll notice that, again, the reason cosine has the graph that it does is, again, its situation with the unit circle, and again winding it in that, again, counterclockwise rotation. And like sine, it will continue on with that, we call in math cyclical, like a cycle pattern, forever and ever to the right, and also to the left. So definitely a lot of repetition in these. Alrighty, so last but not least, let us talk about tangent. So tangent, here we come. You'll notice the same thing with cosine. I kind of skipped a little bit. Didn't want to fill in every single thing, especially with tangent, because you have to do a quick little division. So I picked the ones that will make it easier for us. So let's start with 0. So at 0, we have to do y divided by x, right? So 0 divided by 1, well, that is 0. So tangent of 0 is 0. That's good news for us. All right, pi over 4. We have to do the y divided by the x. Because they're the same thing, something divided by itself is 1. So tangent of pi over 4 is 1. Let's start with pi over 2. So pi over 2 is going to be 1 divided by 0. Can't divide by 0, so that's technically undefined territory. So at pi over 2, we're actually going to leave that blank. There is no dot at pi over 2 in tangents. Let's do 3 pi over 4. 3 pi over 4, y over x. We got a positive divided by itself, a negative of itself. So that would end up getting just -1. So we'll fill in a -1 here. Pi of this, let's see here, is going to be y divided by x. So 0 divided by -1, which would be 0. So we'll put a 0 here. 5 pi over 4 is going to be, let's see here, a negative divided by a negative of itself. So that actually turns out to be a positive. So that would be a 1. And then let's do 3 pi over 2. 3 pi over 2, -1 divided by 0, or y divided by x. That's another undefined location, so we're going to leave that one blank. And then let's do 7 pi. So 7 pi over 4, that's going to be a negative root 2 over 2 divided by a positive, so that's going to end up being a -1. So we'll put -1 here. And then last but not least, 2 pi. We're back to 0 again. So this divided by 1 is 0. So I'm going to fill that in. Now, this definitely looks a little bit more disconnected. You can definitely see a pattern going on. It definitely 0, 1, skip, -1, 0, 1, skip, -1, 0. The next one definitely is probably going to be a 1 here, and then a skip. So let's fill in tangent, and let's see what a tangent function looks like. We definitely see that there are skips in it, and when there are skips, we know that there will be what are known as asymptotes. So let's go ahead and draw this in. A little bit more of a complicated graph, but as you can see, it goes through each of these dots. Now, if I were to kind of fill in this information a little bit more and get a little bit closer, you would have seen that it definitely curves. But you'll notice that these graphs definitely hug up against those asymptotes where we would skip at pi over 2. So there definitely is an asymptote at pi over 2, at 3 pi over 2, and then it continues every, it seems like every pi, another break in the graph. Okay, so it kind of continues that over and over and over. So a tangent function does not look a lot like sine and cosine, but yet again, it is a combination of dividing the two, which is why it looks so unique. So the unifying factor of all three of these things is that they're all cyclical, meaning they are all pattern-based. They go on forever and ever and ever. I guess the unique thing about this is that where sine and cosine definitely look like they're part of the same family, tangent has kind of a unique flavor of its own. Asymptotes because of the whole 1 divided by zeros as you go around the unit circle. And the fact that it looks almost like little cubic graphs, just copy and pasted all next to each other. So with that being said, these are the three basic trig functions that you will be looking at in subsequent math classes. The assignment today will be just kind of looking a little bit more at depth into sine and cosine. So when you get to, for instance, a pre-calc class, you'll know a little bit, have some background when you go into your trig units in that class. Okay, so hope you guys got a little bit something out of that, and hopefully you at least know a little bit about trig before you move out of Algebra 2. Wishing you all the best. If you have any questions, we do have a few more office hours this week, but other than that, adios. You guys have a wonderful summer. Talk to you later, guys. Bye.